Okay, today I'd like to start chapter 5. Chapter 5 is mostly on naming binary compounds and acids. So today I want to cover naming of covalent binary compounds. Excuse me, the next meeting will be ionic and acids. All right. So let's jump over to okay. Most things in the world are molecules, not atoms. There are a few atoms, those are the noble gases, but mostly elements by themselves typically are unstable for the reasons we talked about in chapter 10, because of their unfilled shells and their actions to fill those shells, either by transferring or receiving electrons or by sharing electrons, forms compounds. And of course, those compounds are all over the place. They're proteins, cells, any kind of matter, inorganic, organic. Our world is, that's what's kind of cool about chemistry. It's in everything. Now, when a compound forms, there's something called the law of constant proportion. Okay, and what I mean by that is the ratio of the atoms within the compound are whole number proportions. For example, water, you always see is H2O. Now the 1 is optional. So 99.9% of the time, this wind has brought on my cough a little bit. 99% of the time, if not more, we leave the 1 off. It's not wrong if you put the 1 down there though. For your consistency, if you'd like to do that, that's fine. All right, however, it's never, no exceptions, 2.1 or 0.9. It's always an integer, always. And that's what they mean by constant proportion. Constant as an integer, whole number, not a decimal or fraction. Now, we can represent chemical substances a lot of different ways. And we went over in detail the VSEPR model, the valence shell electron pair repulsive model, in extreme detail. There are various ways to represent that. Formula always starts off with something like this. AEG are elements, XYZ are subscripts saying how many of the individual atom is present. Frequently, we're going from left to right, we'll have this order down here. Starting with carbon, phosphorus, etc., and ending with the halogens. That's typically what the formulas are. They normally aren't scattered around. If it's ionic, you'll have the cation, the positive ion, before the anion, the negative ion. Okay, 3 basic types of formula. An empirical formula is the simplest, but gives us the least amount of information. And so frequently it's not used. It's used sometimes when we're doing some wet analyses in the lab, but normally it's kind of not used very much. The molecular formula is used a fair amount. The problem with the molecular formula, it doesn't show how the atoms are connected. It just says how many of them. Now, these two differ. The empirical is the simple ratio. The molecular formula is the actual number of each atom. The structural formula is the most useful because it shows some kind of connectivity. For example, if we're looking at the structural form, if we're looking at the formula for acetic acid, usually it's written like this. For example, this ending is for an organic acid. So this shows you that formula is an acid. This doesn't, it doesn't say anything. It just says how many carbons, how many hydrogens, how many oxygens. And as we knew from last chapter 10 stuff, that there are 8 versions of structures that meet this formula, C2H4O2. This is one of them, but that's not the only one. In fact, this is, if you do the Lewis dot structure here, it would look like that. That's one of 8, though. This tells us it's that one. Here is the CO2, COOH, and acetic acid is one of the smaller organic acids. Another concept we've talked about already are isomers. Now, for example, with the following molecular formula, we can draw 2 alternative Lewis structures, one with the OH on the end and one with the oxygen in the middle. They both are legal Lewis structures, but we don't know which one it is. This is called an ether. It's usually referred to as dimethyl ether. And this is an alcohol. Alcohols have an OL ending on them. Alcohols act chemically very different than ethers. So we would have these 2 alternate formulas, and we'd have to do some testing to figure out whether that is an alcohol or the ether version. Hence, they're called an isomer. Same number of atoms, different structure. And again, these have to be legal structures. Okay, now a mechanical model we've already looked at in chapter 10, and then there is a Lewis model and a valence shell electron pair version as well, the VSEPR version. That's where we get into the tetrahedral and trigonal pyramidal and trigonal planar, etc. If you have a models kit, frequently the atoms will be color coded. Okay. The molecular formula, all it says is how many actual atoms. Structural formula gives us an indication of the structure. A ball and stick model is supposed to be a 3-dimensional version, as well as space filling, a 3-dimensional version of what the molecule looks like. Space filling is used a little bit. It's not used a whole lot. Ball and stick are used frequently, and structural formulas are used frequently, but the structural formulas are usually written like this, though. And that is supposed to represent that, where the triangle is coming out, the dotted lines go into the page. Okay, nomenclature. Okay, we're doing covalent ionic molecules and acidic. We are going to cover just the covalent today. Tomorrow we'll get into the ionic and acid. All right. Excuse me. An atom is made of, an atom is made up of an element, one element. A molecule is made up of multiple elements. Diatomic means there are two elements in there. And diatomic also means that there are two identical atoms as well. There are 7 of them, and you need to know these. Okay? These are the 7 here. Basically, the noble gases, and oxygen, nitrogen, and hydrogen. Okay, except that one there. All right, and when you name them, all you need to say is hydrogen. These are also gases. Now you don't have to say hydrogen gas. It's okay if you do. At room temperature, these are gases. But you can say hydrogen gas or hydrogen. And if you're talking in text in terms of a molecule, you can say hydrogen, and it's known that hydrogen exists diatomically. I always like to say hydrogen gas just to make sure everyone's clear on what I'm talking about. Now, molecular compounds are covalent compounds. That are bonded covalently. They're the non-metals. So when you have non-metals bonding covalently, non-metals can also bond ionically. When we have 2 non-metals together, okay, so we have a non-metal bonded to a non-metal covalently, we are going to name them a certain way. As opposed to if we had a non-metal and a metal bonding together ionically, that is a different naming convention, which we'll cover tomorrow. Okay, so we have a non-metal bound to a non-metal, like oxygen to oxygen, or hydrogen to oxygen, or nitrogen to okay, all those are non-metals binding to themselves covalently. Okay, so we need to use some prefixes, 1 through, you need to know these, 1 through 10, mono, di, tri, tetra, etc., up to 10. And they're going to say how many of the non-metals are there in the formula. For example, here we have 2 silicones, 6 chlorides. 1 silicone, 4 chlorides. Now, let's name that. We all know that's water, but let's name it using the official IUPAC naming. IUPAC this stands for the International Union of Pure and Applied Chemists. In other words, it's internationally known. This is not known as water internationally. It's aqua in Spanish, water in English, and all different languages. You know, you go to Morocco, for example, that's not going to be water. It's going to be named something else. But the IUPAC name is going to be the same in all countries. Excuse me again. Okay, so we have two atoms. One is hydrogen. As it appears in the periodic table. And then chloride, oxide. And that you're going to be adding an IDE. Now I've included a common ion chart. And this is what the ides you're going to be using for the second part of the molecular name. Okay. All right. So first thing you go, the name as it appears in the periodic table, hydrogen. The ide version of the second atom. So that's hydrogen oxide, but there are two hydrogens. So that means that's dihydrogen. And there's one oxygen, so that's monooxide. Now, because there are two vowels together, we eliminate one of them. So it's monoxide. Dihydrogen monoxide. Now, if you have one in the beginning, for example, this silicone tetrachloride, you can leave off the mono if it's in the beginning. If it's for the second atom, you have to put the mono in. Okay, so the mono in the beginning is optional, but it's not for the second one. So the monooxide has to be there. So this comes from the periodic table. This comes from my common chart below, which you can have, by the way, for the test. For next quarter, for Chem 400, you're going to have to memorize these. So if you want to memorize them now, that's fine. They won't be needed for the upcoming test next week. All right. Okay, so we have silicon chloride. It's di. Hexa. Silicone is in the periodic table, and it's an ide. Periodic table and ide. And the mono and tetra reflect how many there are. Now, if there is only one element in the group, not two. For example, this O5. Okay, you're going to name it like there is nothing here. So you're going to name it as an ide. Trinitride. Okay. And remember, when we have two vowels together, we eliminate the first one. So that's pentoxide. Instead of tetraoxide, it's tetroxide, trioxide, monooxide. Okay. And it only applies to the A and the O, not the I, like in tri. Okay. So let's name all these. We've already named water. This is going to be dihydrogen dioxide. So this is the IUPAC name. Okay, this is going to be mono nitrogen trihydride. And the mono, remember, is optional. This is going to be dinitrogen oops. Tetrahydride. This is going to be carbon tetrahydride. By the way, these are not common names. When you get into OCHEM, this is an IUPAC name, but it's not. It is a common name also, but it's okay. So this is going to be well, and this can be mono, optional mono, dicarbon. Hexahydride. This is going to be mono phosphorus trihydride. And this we're going to go to the periodic table to get. Yeah, that mono in the beginning, remember, is optional. Okay, so whenever we have non-metal to non-metal, those are bound covalently. And we're using this IUPAC accepted naming convention. We need to say how many of each element via this numbering, mono, di, tri, etc. And we're going to get into ionic compounds tomorrow, and that's where we have a cation and an anion. And those are bound ionically. And unfortunately, there's a different system for naming them.